to speak at KubeCon. It's our first KubeCon, and this is our first time in China, and we are really excited to be here. Um, Basically, we have been here for the last few days, and it's been amazing. And obviously, not being on call is amazing, and it's been a while. My name is Vijay Dhama. With me is my colleague, Giri Kuncoro.
We're both engineers from GO-JEK, a ride-hailing app from Indonesia. Today, we're going to be sharing our experiment results on benchmarking various container network plugins. Here's the agenda for today. We'll start off with the overview of various CNI plugins, just to get you guys aligned. And we'll be sharing what kind of motivated us on doing these experimentations, in what kind of environments we conducted the experiments on, and what are the results that we got from these experiments. And then finally, what are the key takeaways that we can learn from our experiments. Vijay will start with a brief overview of various CNI plugins that we used to conduct the test.
Okay, a brief overview of Kubernetes network model before we start with CNI. It's just Kubernetes network model is meant to be quite simple. Every container should be able to talk to every other container without being NATed or traffic bridged through. And all nodes should be able to talk to every other node without being NATed. And basically, whatever the container IP the other container sees is what is the container's IP. So the implementation itself of networking is not done in Kubernetes. It just provides an interface through CNI for other plugins to implement and plug in into your Kubernetes implementation or deployment. Next is just a brief overview of what CNI does. CNI provides two things. It provides connectivity and reachability. So connectivity is simple as just provisions or the network interfaces of the containers or pods. And second part is reachability, which is done by the daemon that is basically the CNI plugin. It provides you with a way of reaching from one pod to another pod, or basically one pod to a service and all that. There are lots of CNI plugins around. This is a link down below where you can find the number of CNI plugins that are actively maintained. There are actually a few much more than that, but these are the listed CNI plugins that you can take a look at. The CNI plugins that we're going to talk about are Flannel, Calico, Weave, Cilium, KubeRouter, AWS CNI, Copio, and Romana. Starting with a brief introduction to these CNI plugins. So I'm going to just run through these. Flannel is just a simple L3 based on network fabric, which provides a bunch of support for support for a bunch of backends, including VXLAN, which is a default in Flannel, and it also supports other things like you can set up AWS VPC network fabric within Flannel and even GCP network. Second is Calico. Calico is a basically L3 approach for using CNI. It also provides a default support for BGP, and it also provides native support for network policies. Not all CNI plugins do. Next is Weave. Weave is a product from Weaveworks. It is a CNI plugin that works on nowadays works on OVS module, and which is called something called fast data path, and does provide support for encryption and network policy. Next is Cilium. Cilium is a BPF-based CNI plugin. It has extensive support for network policies, even greater than Calico and Romana. KubeRouter is a simple IPVS-based CNI plugin. It does simple networking. It doesn't provide support for overlay networks, and it does host-based routing. AWS CNI provides support for basically configuring your Kubernetes cluster within the AWS VPC network fabric, so you can provision your Kubernetes cluster to have IPs from the AWS VPC itself, and just directly have a custom workload running wherein you can talk from a VM to directly to a pod without going through service and all. Cop.io is another VXLAN-based CNI plugin. Supports L2 with GRE and IPsec for encryption. The last one is L3, basically Romana. It is also a L3-based CNI plugin, which works with BGP or OSP. Next, we're going to go through experiments, which Giri will go through.
Let's now see kind of experiments that we did. We started with curiosity on each of this plugin because there's just so many, and we started to play around with each of those and conducted some performance study, some simple performance study on each of this. When we were conducting this experiment, we had 4 goals in mind that motivated us in doing this experiment. First, we wanted to see which CNI plugin that offers the lowest latency and which one has the highest throughput as a typical performance network benchmark started. And then we wanted to evaluate CNI plugins performance with different protocols, network protocols in this case, TCP and UDP, as well as how do they perform with various packet sizes. And the third one, we wanted to see how much each CNI plugin consume, how much CPU do they consume, and how much time do they take to provision a container network, for example. And then lastly, we wanted to evaluate whether there's an impact of Kubernetes network policies in network performance. These are the environment that we did in conducting the experiment. We spawned 8 Kubernetes clusters with different CNI plugins. We set this up with a minimal node size. It was a 2-node cluster. The master node we tainted so that we could spin up workloads in it. The size is M4X large in Amazon AWS. We chose AWS because we cannot use Google Cloud here in China. You know that. We use Debian 9 distro and kernel 4.9. We use COPS to help us spin up the clusters with version 1.10.9 when we were doing the experimentations. These are the version of CNI plugins that we leveraged to conduct this experiment. An important note here is we treated each of the CNI plugin as a black box. So we didn't do any specific tuning or custom configuration with each of the CNI plugins. So we were just using the default configuration that they provided as documented in the Kubernetes IO docs, as well as I think included in COPS. We used 3 tools to conduct these experiments. First, we were using SOCPerf to measure throughput and latency. And then we use NetPerf, particularly their specific feature called UDP-RR to help us measure the CPU utilization that each CNI plugin consumed. And lastly, we were using a simple Golang-based tool implemented by our friends in Pandey Networks that help us in simulating HTTP workloads and measure response with various network policies. We then conducted 5 different experiments in 8 Kubernetes clusters. Our first experiment is on throughput and latency, which is pretty basic. In this case, we were running SOCPerf client pod in node A, the first node in our Kubernetes cluster, and SOCPerf server pod in the second node, or node B in this case. We then configured the packet size to be fixed 256 bytes for TCP throughput tests, as well as 16 bytes for the TCP latency tests. We use host network without any CNI plugin to be our baseline. As can be depicted by this picture, this is our TCP throughput result or graph. The red bar on the left side is our baseline, which is also depicted by the line graph in a nice pink color as our baseline. As you can see here, all of the CNI plugins suffered TCP throughput loss, obviously, because of their mechanism, right? Some of the CNI plugins do packet encapsulation or overlay networking. Some does routings, etc. Particularly for Flannel, Weave, CopeIO, Romana, they suffer speed throughput a bit less, around 15 to 20% here. For overlay networks, network performance hits are understandable because they need to traverse the network stack back and forth, right, to do the packet processing. For instance, the packet decapsulation gets invoked at host operating system whenever host OS meets the encapsulated packet at L4, for example, and then the packet will get transmitted to the pod through Ethernet interface, which will then traverse the network stack again. For Weave, the result here is very interesting because it is pretty close to the baseline. I think the closest to the baseline. Weave came up with, I think, an interesting feature called fast data path around last year, which is essentially using the data path module of OVS in their implementation so that they could decrease the number of network traversal, in particular decrease the traversing between user space and kernel space, basically. This was also documented in their Weave documentation. They could improve the result of their performance around 3 times compared to their old implementation. For this 4, Calico, Cilium, Kube router, AWS CNI, unfortunately, they suffer significant loss in our study. We were actually expecting a much better result by Calico. However, apparently in the default config that they have in Calico, they still configured IP and IP encapsulation as default. So that's why we can see the result here for Calico. Here's the result for our TCP latency study. Overall, most of the plugins added around 25% on average latency, additional latency here. For AWS CNI and Romana, they suffer latency the least, additional latency the least, because both AWS CNI and Romana actually talks to AWS VPC fabric on the network backend. That's how the packets are relatively faster to travel compared to the other CNI plugins. For CopeIO, the latency is doubled at least compared to the baseline. We haven't conducted a detailed analysis yet, so if you want to help us, please come meet us. Our second experiment is on different protocols and different packet sizes. So it is important to pick appropriate network protocols to get a desired, for example, quality of service in our system. And then packet size here plays an important role in a network performance because, for example, given sustained data rate, a larger packet size will give less number of packets being transmitted. And on the other hand, a fixed packet being transmitted for a large packet size, it will give us a larger data rate. We did a similar experiment to what we did in the first experiment. We ran sockperf client pod in the first node, and then sockperf server pod in the second node. However, the difference here is we measure both for TCP and UDP throughput, and then we increase the packet size from 16 to 256 bytes. Here's the result of our TCP throughput study. The x-axis is actually the different packet size from 16 to 256. As you can see here, only half of the CNI plugins could scale as the packet size increase. In particular, Flannel, Weave, CopeIO, Romana could scale the TCP throughput well, pretty close to the baseline as the packet size increased here. However, for this 4, we could see here, they suffer considerable loss, especially when we increase the packet size from 128 to 256, the throughput level is quite similar here. For UDP throughput, for obvious reason, in general, including the baseline, they provide less UDP throughput because of obvious reason. In TCP, we could actually make the physical link more efficient, right? By design, it's like that, their mechanism. However, the difference here is all the CNI plugins could actually scale given different packet sizes. Although the throughput loss is considerable, but the point is CNI plugin could scale as the packet size increase. Being AWS CNI and Romana suffer the least throughput loss for UDP, actually. Our third experiment is on the CPU overhead that each CNI plugin introduced to Kubernetes. We were using NetPerf, a pretty famous tool for performance benchmark. We particularly use their unique feature called UDP-RR, which is utilizing UDP to measure CPU utilization of each of this plugin. By using this UDP-RR, we could measure the time spent in user space, kernel space, and waiting for I/O. Here's the graph. On the two graphs on the left side are actually CPU utilization, and the two graphs on the right are CPU time or service demand. The service demand means time that is required to complete one transaction of UDP. With this, we could actually show the cost of CNI plugin from the request side or client side. As you can see here, most of the plugins, in fact, all of the plugins introduce CPU overhead, but it actually varied from the least is around 10% to 40%, because they need to, obviously CNI plugin, they need to allocate some IP from IP pools, they need to do in-cap, decap, they need to talk to AWS VPC API, for instance, for AWS CNI and Romana, etc. However, an interesting result here is these two CNI plugins, which is Weave and Cilium. They, for Weave, the Weave adds around doubled the CPU overhead compared to the baseline, and Cilium at least tripled the CPU utilization here. For Weave, we think because of the OVS, probably, and their software routing, because they do routings, they do peerings, and they could save network partition and cluster and things like that. Most probably add additional computation. And then for Cilium, they leverage the BPF module in kernel. Every time they need to generate the byte, right, and then inject it to the packet flowing. So we thought that adds up the CPU more. If you have a better analysis, please come to me. The fourth experiment, we were looking into how much time does a CNI plugin use to provision a network whenever a new pod being created. So network launch time is very important in case you guys have a short-lived or latency-sensitive workload in your Kubernetes cluster, right? So we measure the time when kubelet issues container create command or pod create command in this case. In the example, kubelet is trying to spin up Nginx pod on the left, and then until the Nginx pod is responding to pinging requests from the pod on the node B, we stop the stopwatch. So it is the time from container create command until it responds to the pinging request. We understand there might be an overhead here because kubelet is polling events to the kube API server here. However, we didn't figure out a better way to measure this, and I don't think this will cause issue because the comparison between CNI plugins are apple to apple. Here's the result. For some reason, Flannel took more than 10 seconds to spin up the network on a pod. So in order to make graph prettier, I'm going to take this out. Most of the plugins add additional network launch time. For this 4 CNI plugins, add around 0.5 to 1 second additional network launch time whenever kubelet creates a pod. Keep that in mind that network launch time doesn't include the image being downloaded because the kubelet state comes after that. The kubelet container create states comes after the image download. Also for these three, Cilium, kuberouter, and kube.io, they add additional 1 to 1.5 second. Our last experiment is on whether there's an impact of network policies to the network performance. In our reference, in a typical network performance benchmark, there's no application logic running in the host level. So this leaves the host CPU to be available to process whatever networking required in the host level. So with this, we make sure to run a network policy test that doesn't saturate the network as well as saturate the CPU. This has impact of isolating the network policy process by the CPU at host level. So we are borrowing a tool from our friends in Pani Network. We run the tool, the client pod in node A and server pod in node B. We then configured the client pod to send a fixed rate of 2000 SP requests with a rate that we ensure do not saturate the network as well as CPU. And then the server, we configured with various response size from 1 kilobyte to 100 kilobyte. And then we make sure each request is performed in a new TCP connection by disabling the persistent connection. In case you guys are using Nginx, this could be achieved by disabling the keep alive configuration, for example. And then we repeat this test for 0 to 200 network policies. What this means is for 0 network policy, we do not run any network policy, obviously. But for instance, I'm giving you an example of 200 policies. In this case, we configured the first policy as default deny. This will disable all traffic coming into the server. And then 198, we generated a policy, a random policy. For instance, in this case, allow ingress to port A, allow ingress to port B, ABCD, random port, which do not match the port that the server is listening to. Then the last policy we configured with port 80, which will allow packet to coming in and matches the port, basically. In this case, we could simulate that the traffic, all the policies are being hit before when we were doing this test. Here's the result. For Calico network policy, there's no meaningful delay at all being introduced in the response time. At max, around 0.1 millisecond, we could notice very slightly for 100 kilobyte response there when we tried to increase the number of policies from 50 to 100. And then for Weave also provides us with a similar result, which is a non-significant additional response time here. For Cilium, also similar result, probably around 0.2 millisecond for the blue one. However, keep in mind that the network policy that we tested with Cilium is actually the native network policy feature that offered by native Kubernetes. Cilium actually provides a much better way by providing us a custom resource that they have called Cilium network policy that we didn't test here. For that custom resource, they actually extending what native network policy can offer. The native network policy can offer network policy in L3 and L4 for complete ingress and limited egress. But for Cilium network policy, they could offer L7 as well with complete, much better egress feature. For kuberouter, again, similar result. A little bit higher, but still not meaningful. They add additional 0.4 millisecond additional response time for the green one, which is 100 kilobyte response. We did not test the other CNI plugins because obviously not all CNI plugins offer this network policy feature. For Romana, they actually provides, but because of an open issue in GitHub, we could not play around with the network policy when we set up with COPS, because I think the latest COPS release somehow changed the default IP tables configuration that caused some issue with Romana network policy there. Vijay is going to share what are the takeaways that we can learn from this.
Okay, so for takeaways, starting with the CNI itself, in general, very tricky to pick appropriate CNI plugin in general because it totally depends on the use case and where you are running that particular Kubernetes workload and Kubernetes cluster. There are a lot of trade-offs to be taken into account, including performance, security, and isolation. So if you need network policy, then you are going to look into something like Calico or Cilium and perhaps Romana. In terms of what works better on throughput, with default config, Flannel, Weave, and Romana achieve much better network performance than the others. In terms of the larger throughput, obviously TCP has much larger throughput than the regular UDP workloads, which is usually not much for most of you perhaps. Most CNI plugins scale better in UDP, but the takeaway here is you'll definitely have some considerable amount of loss because it's UDP. Most CNI plugins introduce some CPU overhead with Weave and Cilium being the largest. Weave is because we think it's because in Weave it uses the OVS module, which is probably the cause for that CPU overhead. In Cilium, it's I think the underlying BPF module, kernel module that is the reason for that CPU overhead, but that's just a assumption right now. So also in terms of network launch delay, there is a reasonable network launch delay to launch containers, except for Flannel, which I think in this particular test case was an outlier and wasn't totally expected. For network policies, there is a non-significant delay in the basically delay that is introduced on the number of network policies you add. Yeah, so that is mostly our takeaways around the policies. For the experiment itself, we need a more comprehensive analysis, which will basically prove or add more info to what can be done to improve particular CNI and all, and have a much better picture of differences between CNI plugins. For example, we can configure some CNI plugins to work much better on bare metal and bare metal workloads than we can do on cloud providers. For example, Calico, you can disable IP and IP mode to just use BGP, and which we think will offer much better performance. Another experiment we are thinking of is doing concurrent requests and testing all the CNI plugins against those and see what is the performance and TCP throughput and latency responses from CNI plugins. And another test is workload interference, wherein if you already have some workload running on your Kubernetes cluster, you can run these tests to figure out how does CNI plugin get affected due to existing workload and all. We had a lot of references for preparation of this talk. Main three of them include an analysis and empirical study of computer networks, comparison of networking solutions for Kubernetes from Machine Zone, and high performance network policies in Kubernetes cluster from folks from Funny Networks. We had few help from people as well, including Ajay, Gatano, Ali, and Samudra. Yeah, thank you. So this is our contact details. Please reach out to us if you have any details to add to what we can do to improve the comparison.
谢谢.
Any questions?
If there's any questions, or we can chat after this.
So one question, for network launch time benchmarks, so how you get the benchmarks for launch time?
So your question is, how did we conduct network launch time, right?
Right.
How did we measure?
For the
So as you can see here from this diagram, we actually have a stopwatch. I mean, stopwatch. And then when you deploy a pod, typical Kubernetes thing, right? Kubernetes scheduler will actually annotate that somewhere in the Kubernetes state, and then kubelet will watch that, and then say that, oh, I need to spawn the pod that is not running yet in my node. So when kubelet has its own state, state ABCD, one of them is including container scheduled, and then container should be downloaded. Then after this, when everything is ready, there's a state in kubelet that says container create. When kubelet reaches this container create state, and then we start the stopwatch, we start the timer, and then the pod, the Docker images already exist, right? After that, because before that, then pod will run, and then when the pod is running, CNI will provision whatever network required, right? Assign IPs, for instance, routings, talking to etcd, for instance. There's a bunch of mechanisms there, depending on CNI plugin. And then at some point, the pod will accept connectivity. The two things that CNI provide in the beginning, reachability and connectivity. From the second node, we just spawn a ping request. Then when this pod starts receiving the ping request, we stop the timer. So those time. Pod only, not no service, yeah, pod only. Yeah. Does that make sense? Anything else?
When you are conducting the experiment, do you suffer any package loss or something because of the?
Sorry, can you repeat?
Do you suffer package loss?
Do you suffer any package loss or?
Packet loss, right?
Yeah.
So he's asking whether there's a packet loss when we were doing this test. What is the answer?
For packet loss, we didn't actually identify any packet loss. For UDP experiment, we did actually get a lot of packet losses, which is acceptable because it's UDP and not TCP workload. But we, per se, for our experiments, didn't see any packet loss.
Because the packet size is also pretty low, which is 256. Probably depending on the type size, right? Depending on the instance type, when we increase to 500 or 1,000, we will see that. But we didn't do it, unfortunately. Okay, I think the time is up. Thank you so much for attending my talk.